This lecture is going to cover ideas related to homework 34. So this is the last topic of the semester. And I want to describe uh, an important idea about light that comes up in many of the other classes that you will be discussing. It's sometimes described as the photon model, and I want to connect the idea of the word photon and how you might have heard it in other classes with the way that we've been describing light and electric fields and magnetic fields in this class. I think a good way to um, understand our um, to structure the ideas here is to try to answer the following question, which is why do our eyes only respond to visible light? So there's types of light, radio waves, infrared, ultraviolet, X-rays that our eyes never see. And it's not as quite as simple as saying that, for example, infrared light doesn't have as much energy. That's kind of true, but it's kind of not true. If you add it all up, there's more light in the form of infrared light surrounding us than there is invisible. And in part, that's because infrared light covers so many different wavelengths. But it's so I want to try to peel out some of the subtlety. The idea that there's visible light has more energy is not. It's kind of right and it's kind of wrong. It's a little more precise, or we have to say it in a little more precise way. So I want to begin with the model that I've been encouraging you to think of so far, which is light is a wave of electric and magnetic fields. And we've seen this before where the electric fields here are represented as red arrows and the magnetic fields are represented as blue arrows. And a changing electric field creates a changing magnetic field, which creates a changing electric field, and it's a chain reaction that moves through space. And that is what light is that chain reaction of changing electric and magnetic fields. Okay, so we can use this to explain, for example, the double slit experiment that we started the semester with. Send light through two small slits, closely spaced, and we get this interference pattern caused by the electric fields destructively interfering with each other. If we look up close, we get this view. You measured this pattern in lab. However, this isn't possible for us to do in lab, but it is possible to do with very, very sensitive detectors in very, very, very dark rooms. If you decrease the amount of light that is going through the double slit, the pattern gets dimmer and dimmer, and if you are very, very careful about it, we observe that the dimness has a weird character when we get to very, very low light levels. What happens is that the light will trigger an effect, creating dots on our detector where light has triggered a detection, and that at very low levels you can kind of make out the interference pattern, but kind of not. And this idea that light is triggering events in a way that's similar to the interference pattern leads us to the following conclusion, or it leads us straight into quantum mechanics. So, broadly speaking, quantum mechanics says that some properties of light cannot be explained by using the model of the electromagnetic wave. Also, not related to what we're going to do in this course, but nearly all properties of electrons and atoms can also not be explained by treating them as small point masses that are orbiting each other. So quantum mechanics broadly says that everything is described with waves. So visible light has a wavelength vaguely around 600 nanometers. Electrons, the way that we encounter them in everyday life, have a wavelength of around 1 nanometer. Protons, as we typically encounter them in atoms, have a wavelength of about 1 femtometer. So that's the first idea. The second idea is that these waves interact with each other, but they don't interact. They interact with each other in an unusual way, in quantized amounts. quantized means discrete or indivisible, not being able to be divided. So, for example, the electron is a wave, but it's a wave that you can't chop up. There's a smallest amount of that wave, and that smallest amount is what we normally describe as the electron. The proton, it's a similar thing where it's described by a wave, but you can't chop it up into smaller and smaller amounts. There's a smallest amount. The smallest amount of mass is the mass that we describe as the proton, 1.67 times 10 to the minus 26 kilograms. And the electron, the smallest amount of charge of the wave of the electron is 1.6 times 10 to the minus 19 coulombs. So for light, it's a little simpler because light doesn't have a mass we need to describe. It doesn't have a charge we need to describe. The property we care most about with light is energy. So we still describe it with a wave, with an electromagnetic wave, that same picture that I've been presenting for earlier homework assignments. But now, when light interacts with atoms, like when it gets absorbed or when it gets produced by atoms, it can't do that in just any amount of energy. There are indivisible amounts of energy that can be exchanged between the electromagnetic wave and the atoms that are absorbing or producing the wave. So the smallest amount of energy depends on the wavelength or the frequency. The two equations that you can use to describe the smallest amount of energy are shown here. For visible light, it's most common to describe light using wavelength, like 500 nanometers or 400 or 600 or 700 nanometers. And so the lower equation here is the one that ends up being more useful. H here is called Planck's constant, and it's given on the inside front cover of your textbook. I also give the value here in standard units. So this equation allows you to calculate the smallest amount of energy that an electromagnetic wave can exchange with, say, an atom. Okay, so now I want to return to why we see visible light. Some of you may have studied this in the biology and chemistry in more detail in other courses, but the broad idea is that light enters your eye, goes through the lens, gets focused onto the back of your eyeball, the retina. The back of your eye the retina, has a series of things called rods and 3 types of cones, oftentimes described as blue cones, green cones, and red cones. Rods, we react to very, very dim levels of light, and qualitatively are associated with like seeing the brightness, or like they don't allow you to see color, but they can let you see dim things. And then blue cones, green cones, and red cones allow you to see color. So the key idea here, the physics that I want to get across, is that the blue cone curve here has a peak of around 450 nanometers. If you imagine plugging that wavelength into lambda in the equation on the left, with h and c, c, by the way, is the speed of light, 3 times 10 to the 8 meters per second. If you plug in 450 nanometers for a wavelength, you'd get an energy, and that energy represents the indivisible amount of energy that blue light can convey. And blue cones are somehow, through the chemistry and biology, constructed that they only react to the amount of energy associated with blue light, this smallest indivisible amount that blue light can exchange. If we have a shorter wavelength or a longer wavelength of light, then that light will have a different amount of energy, indivisible, that it can exchange, which would mean that if, like, the shorter wavelength, let's say it's shorter wavelength of light, let's say 380 nanometers, which is the left end of that graph, a shorter wavelength would mean a smaller wavelength, which would mean U would be larger, so the indivisible amount of energy would be larger, and it would be, for blue cones, the wrong amount. That is, blue cones, in a sense, are designed that they can only respond to certain energy packets, and if you have an energy packet that's too large or too small, The blue cone simply doesn't start its chemical chain reaction. Um, so, and something similar is true for green cones, except green cones are designed, well, not designed, but they have a structure that responds. You can see in the graph roughly between 500. The peak response is between 550 and 600 nanometers, and then red cones are at longer, between 600 and 650 nanometers. Mostly, that's where the best response is. So each cone is designed to only respond to certain energy amounts, and different types of light can only exchange certain energy amounts. So, for example, blue light has its indivisible energy is greater than red, which has a longer wavelength and lower U, a value for U. And so if blue light hits a red cone, the blue light has, in a sense, is trying to exchange too much energy, and the red cones are incapable of accepting the larger amount of energy. Just to be clear, or I want to, the idea that like how the cones can only accept certain ranges of energy is actually a really complicated question. I wish I could give you a simple, quick explanation for why. I've spent significant time talking to biology and chemistry faculty to try to get a 30-second answer for why blue, red, and green cones are the way they are, and I do not understand it well enough to summarize it in 30 seconds. So the word photon is the what we associate with this indivisible smallest amount of energy that light can exchange. So the photon model of light is, in summary, like the idea that light can only exchange in indivisible energy packets. That indivisible energy packet depends on the electromagnetic wave's wavelength or frequency. So that's the equation in the lower left corner here. And it's a assumption, it's an extra idea added to our model that just happens to be true. It happens to correctly describe what we see. So if we return then to the original question of why can our eyes only respond to visible light and not, for example, infrared light, where there's lots of total energy in infrared light. There's the electromagnetic waves that have wavelength, say, 10 microns, which is smack in the middle of the infrared spectrum. There's lots of energy there, but it comes in energy packets that are quite small because the wavelength is quite large. That small energy packet doesn't trigger the chemical reaction in our rods and cones in our retina. And that's why we don't see infrared light, even though there's lots of total energy in infrared light surrounding us. It doesn't come in, the individual packets are too small to trigger our retinas. Okay, let's stop there.